Okay, welcome. This video is I guess we'd call this knock sensor action reaction, and I'm basically looking at you see a still scope screen. You see 4 channels on the scope. This car's been driven and the road test has been recorded, and basically we see 4 signals. The blue at the top is a crank sensor. Red, the second channel is the ignition trigger for cylinder 1. I'll open this up. As you can see, that's red. Green is the map sensor. Basically, it's our 0 to 5 volt map sensor, and gold is our knock sensor. And that channel's been AC coupled. And this is a 4425 Pico with isolated grounds, and I keyed in on the knock sensor on channel D with its own individual ground and a wire at the knock sensors. You can see knock sensors are piezoelectric devices. They create their own electricity. They react to noise and vibration and knock and things like that. But nonetheless, you can see it right here. In this video, I took about a 90-second recording on the scope, and I drove it pretty hard. I mean, put my foot into it and in and out of it. I didn't hear any audible knock from my ears. But nonetheless, we may not. We just basically, the gist of this video is to see the action reaction of the knock sensor with load and timing and RPM. And I will create a math channel for, I guess I'm going to call it de facto RPM. It's going to be the frequency of the crankshaft of the crank sensor. And so you'll see that once I create that. I just want to talk a little bit about knock. Knock is something that the engineers want to mitigate. They have to deal with it. There's a lot of variables, things that cause knock. Could be running excessively hot. It could be lack of EGR. Could be hot spots in the combustion chamber. Could be crappy gasoline. It could be just driving the car too hard. Some cars will reach the threshold and knock quicker than others. Some cars, I've driven cars that they actually allow a little bit of knock, and the knock sensor senses it and it cuts back the timing. So in this video, we're gonna talk about you're gonna see where the timing is. We won't necessarily see a true cutting back of timing because of knock. We'll just see the relationship of the amplitude of the knock sensor as it changes frequency and amplitude with speed and load, and then how the timing is affected. So that's why we set up these 4 channels, and we'll see that as I go down the line. I will get back to let me get back to the first capture, and then we'll go down the line and we'll kind of create a situation. Right here the car is idling, and this is basically our idle speed. I'll get that for us. Where are we as far as idle speed? We're right here. We're about RPM right down here. We're about 748 right here. So that's just pretty much idling. And let's kind of take a look at just what the knock sensor looks like when it's just the car sitting there idling. I'm at a stop sign here, ready to go. This is kind of what the knock sensor looks like. It has amplitude and it has frequency. Right here, and it reacts differently at different spots. It's a very sensitive sensor. We got about 256 millivolts peak to peak here, a little less here, a little more here. If I key in on the frequency, we'll start to see that's frequency. I'll set up a measurement channel, and you can do this at any spot, usually in the capture. Add measurement for D. No, I want D. Frequency, and between the rulers, okay. And let's get it and see what our frequency is here between here and here. Okay, we're seeing a frequency of about 10.8 kilohertz. So nonetheless, that's basically how the sensor's reacting. The car's obviously not knocking here. It's just kind of reacting to. It's going to react to the load. Here, my right foot starts to get into it. You can see this is the map sensor, and we can start to see we get a little more amplitude in the knock sensor. It becomes more reactionary to the situation. So kind of, I'm just going to stop right here because you can see the load starting to change. The map, I'm going to give a little vertical zoom on the map so we can, okay. And I'm going to do something else. I'm going to create something. I'm going to create what we call, I wouldn't call it directly an RPM math channel. I would call it a kind of a wannabe RPM math channel, good enough. I don't know how to create an RPM math channel, to be honest with you. This is going to take the crank sensor, and I'm going to go to tools. I'm going to go to math channels, and I'm going to, right here, I created this. And you'll see, I go, okay. And now we have in black, that is a frequency of the rotating wheel, the crank trigger wheel, which has about 14 or 16 teeth. So I'm dealing in kilohertz. So I'm at between 300 to about, I set it up to about 300 and 900. I find that a good spot to where I can get the whole range of the capture so you can see the difference in RPM. This is not an RPM math channel. It sort of is frequency. That's why we're going to deal with this little top notch here. Nothing we can do about that. That's the encoded portion of the crank sensor, which the math channel is reading. But nonetheless, we can see that black signal swing up. That's pretty consistent with the map. When the RPM starts to increase, we see a little more amplitude on our knock sensor right here. So as we roll down the road, I got my foot into it. Okay, this is where I kind of gave it some beans. You can see the RPM RPM kind of going up, the map sensor going up, and I decelerated here. I probably took my foot off, and we can see the knock sensor. The knock sensor is pretty active. That's a pretty thick looking representation of the knock sensor. As we go to the next screen, we'll see what happens here. Okay, RPM comes down. Knock sensor amplitude is kind of descending down to an idle. Again, my right foot got up. RPM goes up. Knock sensor amplitude goes up. And we can see the difference. Let's kind of take a look. Right now, we'll kind of take our first look at the timing. I'll base it right here. You can see this is pretty good load right here. Where are we as far as RPM? We'll get into this. Let's kind of take a look at where we are. We'll look at a fire cycle. Okay, here to here. As far as RPM, let me bring this guy down and let me give some vertical zoom on the crank so we can we're going to look at the timing now. And let me kind of unfilter it, get it a little more. Okay, let's look at the timing. We're looking at red and blue. Okay, let me get the knock sensor down so we can see. Let me get the math channel down or up. We just want to concentrate on our red and our blue because that's the way we'll be able to determine the timing. Right here, let's get a little more, look at a fire cycle. Okay, you can see our ignition trigger for 1 right here. And then we'll go a fire cycle. We'll go 720 degrees. Because there's definitely a relationship between obviously knock and timing, where the PCM decides to put the timing because of the signal it's seen from the knock sensor. So I just want to point out something here. In my other video, we determined that this is that trough. When I did that video called "Where's TDC," and for this crank sensor, I'm going to say 40% across this trough is TDC. And that's with my naked eye, but nonetheless, we're going to get it close to the timing. So I'm going to see the degrees from the strike when the spark was commanded to TDC, and I'll get us to where we are. We're about 4 degrees before top dead center there. Okay, that's could be a decel. Let me see where I was, and let's get an idea where I was. Okay, anyway, that was that condition. Let's get it right here. This looks like let me get back to idle. Let's kind of get an idle timing where we were at idle. Let's get the RPM, and let's determine where the timing is at idle so we know we have a reference of where we are as far as timing. Okay, our RPM is here to here. RPM's about 937. Okay, so let's look at our timing right here. Okay, we want to go from, we got a fire cycle. Okay. Okay, this is a fire cycle, 720 degrees. And as far as timing, we're going to go 40% into that trough so we can see okay, as I said, about 8 degrees. That's pretty consistent for this car. 8 to 10, it kind of finds its sweet spot. We know where that's our timing degrees at idle. Now, the gist of this video basically is this tells us action reaction, the knock sensor, the timing, the knock sensor, the timing. There's other things that obviously affect the timing. The car's not knocking at idle. But nonetheless, the reason I decided to make this video is just if we're ever in a situation where we need a scope to look at that action reaction between the knock sensor, amplitude, frequency, and the timing, and it's going to involve a scope. That's why I decided to make this. But nonetheless, the point I'm trying to make is we never want to sell a scan tool short. Scan tool's really good if we have a knock sensor code or we want to know where the knock sensor is. And most important, I tell you, is if we ever have a lack of power complaint. If we had a lack of power complaint, sometimes, I've seen people get tunnel vision and they start to think about plug catalytic converters and fuel pressure. And being that distributors went away years ago, that we still have a timing that's constantly being adjusted. It has to be. You can't just leave a timing fixed no matter what kind of ignition system you have. If it has points, centrifugal advance, vacuum advance, or a powerful high-speed computer controlling the timing, there's always variables where you have to light that mixture at a certain spot before top of the center, maybe sometimes slightly after top of the center. But you want that flame to burn and give that piston the best push, the most efficient push. So obviously, timing will always be adjusted. But nonetheless, the reason is we could sometimes forget that timing could cause a lack of power. If we had a knock sensor that was hearing something in the engine that we couldn't hear, and the PCM was cutting back the timing, and the vehicle fell on its face, you have to look at that PID. That's really important. You got PIDs like ignition timing on your scan tool, or knock retard, how much the PCM is taking away. I've seen PCMs pull away 26 degrees and the vehicle wouldn't get out of its own way because the knock sensor was sensing something. It was a cam lobe that was pitted, or a lifter that was pitted, and the knock sensor heard that and the timing got cut back. But when the tech drove the vehicle, it was a lack of power. So sometimes you think about, things that cause, fuel pressure, ignition, other forms of performance that could affect that. So just want to be mindful that checking ignition timing on a scan tool is really important, and knock sensor activity. If the knock sensor is sensing something that may cut the timing back. So anyway, we're just continuing to pan here. We can see a difference here. We got the map sensor changing. We got the RPM changing in black. We got amplitude changing on the knock sensor, and basically we looking where are we now? Here we're kind of giving it, I'm giving it some well, I'm on a decel right here. I'm on a decel and I'm back to idle. I'll do one more. You can see our RPM is swinging down. Our load is coming down, and our hash and our knock sensor is sort of lessening. It's on the decline. It's kind of descending here. It's coming back to its sort of idle state. But nonetheless, I'll do one more timing check here, and we'll call it a video. Basically, here we are. There's a fire cycle. Here's our 720. Kind of keying on that. Let's see our knock sensor. Let's get rid of it, and we'll see where our timing is. We'll go 40% into that trough. Now we got about 26 degrees of advance. So basically, this is a way we can look at timing, through the front door, right from a direct measurement, in lieu of a scan tool. But we never want to sell a scan tool short. It's kind of a combination of both. But anyway, we can see our action reaction. We have timing of 26.73 degrees before top dead center. That's evidence right there. Let's get back, and then we can also see our knock sensor, what it looks like as far as its action. So I wouldn't call that a knock, but it's something. Obviously, if the vehicle knocked, we would see the timing get cut back. Cutting back the timing would mean this this red guy here, this trigger would happen to the right. It would happen later or closer to top dead center as opposed to before top center. So it would be going this way. It would happen this way. Anyway, this is Technical Technician from Diagnation signing off. And remember, when you're doing drivability, always check the ignition timing on the scan tool. Thanks a lot.